Hello, everyone. Welcome all the audience to IEEE-PES webinar. Today we got one of interesting topics again. Okay, looks like today we have many audiences. I think 36 now. Okay, 36 people joining our session. Dr. Luca, are you here?
Yes, I'm here.
All right.
Yeah.
Our speaker is here already. Okay, but before that, let me first introduce the topic of this talk. Okay, today the topics of the webinar is distributed energy resource management system for active management of emerging distribution grids. Okay, and first of all, let me introduce our speaker. Okay, Dr. Luka Stisowski is with the Faculty of Technical Science, University of Novi Sad, as an assistant professor, as well as with Schneider Electric as a product manager at the DERMS department. He is also a research affiliate with Case Western Reserve University. His interest is in distribution system modeling, renewable distribution generation modeling, fault calculation, and relay protection in distribution grids and microgrids. With high DER penetration and integration of DERs into power systems and DMS and DERMS power applications. He received the BS, Master of Science, and PhD degrees with honors in power engineering from the University of Novi Sad, Serbia in 2013, 14, and 17 respectively. His PhD research was conducted in a joint supervision between University of Novi Sad and Case Western Reserve University, Cleveland, Ohio. Okay, and I think he got lots of experiences about the MS to share with us today. And I think it's time to open our session now. Dr. Luca, are you ready to start?
Yeah, sure.
Okay,
just
please.
to share my screen. Okay, hello everyone. Dochet and IEEE Thailand, thank you very much for hosting me. And also big thanks to everyone who joined today to listen to this webinar. So today we are going to talk about novel software solutions called Distributed Energy Resource Management Systems, or DERMS software, for active management of emerging distribution grids, or how DERMS software actually enable much needed DNO to DSO transformation. So here's my short biography, but as Dochet already talked about it, so I'm with the Faculty of Technical Sciences, University of Novi Sad, and also with Schneider Electric as a product manager for DERMS and DMS applications. So here's the outline of today's webinar. So first, we're briefly going to tackle how it used to be. So how traditional distribution grids were used to be easily operated by almost completely passive distribution network operators, or DNOs. Then we're going to see a tremendous potential of renewable energy and how this potential rapidly changes the landscape of distribution grids, and with the integration of so-called distributed energy resources, or DERs, which are basically small-scale generating units dispersed all over the grid. So we'll see that there is an urgent need for the transformation from almost inactive DNOs to much more involved operators that need to react and track the conditions in the grid in real time, called distribution system operators, or DSOs. We're also going to see some specific examples of the challenges that DSOs are facing today because of high penetration of DERs. And then we're going to see how novel DERMS solutions actually enable DSOs to overcome these challenges, and even more, to transform these challenges into the benefits for both distribution utilities and end customers. In other words, we're going to see how DERMS solutions enable DSOs to actively manage their corresponding complex and highly dynamic distribution grids of tomorrow. And finally, give some concluding remarks. So let's start with how distribution networks used to look and operate for decades. So distribution grids were completely passive networks with the sole aim of transferring the energy from supply substations, so from transmission networks, to the end customers. So there were no active power resources located in the distribution grid layer. And thus power flow was in a top-down direction from supply substation to the end customer. Thus, traditional voltage regulation devices were located at predefined positions, preset by the operators, and were fully able to maintain voltages inside boundaries without almost any interaction by the operators. Similarly, fault currents were highly predictable and also in a top-down direction from the supply substation to the fault location. And thus protection equipment were located at predefined critical locations and preset to react on highly predictable and unidirectional fault currents. So it was almost set and forget method, where the protection equipment would be set and coordinated upfront once per year or once per season, and fully able to protect the whole grid without almost any interaction by DNOs. So we can see that DNOs were able to manage the grid using simple paper-driven processes without much interaction. So almost no need for any interactive action by DNOs in real time. Now, let's see the tremendous potential of renewable energy and how it actually rapidly changes the landscape of distribution grids. Look at this amazing fact. Every 2 minutes, the energy reaching the Earth from the sun is equal to the whole annual usage of humanity. Think about this for a moment. Just 2 minutes of sun energy that reaches the Earth is enough for the whole annual usage of humanity. So it's amazing. Then the similar story with wind. In this Harvard report, they're saying a network of land-based 2.5 megawatt turbines restricted to non-forested, ice-free, non-urban areas operating at as little as 20% of their rated capacity could supply more than 40 times current worldwide consumption of electricity. Now add the offshore potential to this and you will easily get double or even triple these figures. So we can see the potential of renewable energy, especially sun and wind, is amazing. Now, when the governments around the world realized this potential, and of course, when the technology enabled us to harness this energy, this is what happened. Through various incentives and feed-in tariffs, governments around the world in early 2000s basically said, build as much solar PVs and other renewables as you can and connect them wherever you want. Just build it and build it fast. Especially interesting have become connection of renewables to distribution grids, because to distribution grids we can connect small-scale resources with much less upfront investments. And so this is what is happening. From very simple and easy to manage distribution grids of yesterday, completely passive networks, with the integration of so-called DERs, we are rapidly going to highly complex and very dynamic distribution grids of tomorrow. So on this graph, you can see the report from the Navigant, which is showing the increase of the connection of distributed energy resources in the past couple of years and their predictions for the next couple of years. And it is given in thousands of megawatts, so it's huge. And this integration is rapidly changing the landscape of distribution grids. So now let's see what is considered as DER. First, as we said, every type of distributed generation, such as solar PVs, wind turbines, small hydropower plants, CHP units, or DERs. Then energy storage devices, much needed devices in today's changing environment with so many intermittent sources. Then electrical vehicles and EV charging stations, also DERs. Finally, demand response and energy efficiency programs, also considered DERs. So we can see a high amount of completely novel technologies connected on a daily basis to traditionally passive distribution networks. We can imagine how complex distribution grids are becoming due to an ever-increasing DER integration, and we saw on the previous slide how this integration is rapidly increasing. So in this environment of highly complex and dynamic distribution grids, DSOs first need to provide reliable and affordable grid operations. They need to ensure that the grid operates within technical and operational limits at all times, 24/7, where the conditions in the grid are changing in real time, completely different than it used to be. They need to ensure that the grid remains secure under any unpredictable trips or generation losses in the environment of intermittent sources of sun and wind that are changing in seconds. To ensure the coordination with TSOs, to enhance system security and reliability through the provision of flexible customer services, to actually use the flexibility of customers to enhance reliability and security. Then distribution utilities also need to take care about network investment planning. So they need to identify requirements for grid capacity, so for strengthening the grid in order to host new DERs, or even better, to identify system-wide options for using the flexibility of the existing DERs and the new DERs to avoid new capital investments, but to host as many DERs as possible. We're going to discuss this in a little bit more detail in a moment. So we can imagine how hard this is for DSOs, and it's actually impossible to be provided for such complex systems using paper-driven processes. Now let's see some specific examples of the problems introduced by DERs. First, poor awareness. Without having some kind of intelligent solution that will track the connection of DERs on a daily basis and present it to the DSOs, DSOs are lost. They don't know where are DERs, what's their current behavior, is this going to cause some violations, then what are the forecasts, what is going to happen, and is this going to cause violations. These DSOs need to be aware in real time. Then voltage problems. In traditional distribution grids, we had only a problem of under voltages in deep down in the grid, and they were highly predictable and easy to manage. However, in today's environment, with high amount of DERs, in some periods, we can have also over voltages at the connection points of DERs. And more importantly, these problems are changing in real time. So DSOs need to be aware of them and need to have tools to react on them and prevent them in real time. Then reverse power flow, the new phenomena where first time in history we have power flowing from distribution to transmission in periods of light load and high production of renewables. This can cause protection problems, voltage fluctuations, and even problems to TSOs. So DSOs need to be aware and able to prevent it. Overloads. Are the existing cables and transformers sufficient for new kinds of highly dynamic loads, such as electric vehicle chargers, microgrids, and so on? How to intelligently manage existing DERs to avoid it. Then short circuit levels. Now, short circuit current is not in top-down direction anymore. Now we have short circuit currents flowing all over the place because of DERs. And more importantly, they are not predictable. They are changing in real time. So our protection equipment needs to be adapted in real time. We can't rely on traditional set and forget methods anymore. Finally, integration of new DERs. New DERs are being integrated on a daily basis. So the planning departments in the utilities are facing too many requests which cannot be processed with traditional paper-driven processes. Then are these DERs going to cause congestions? Do we need new investments in the grid assets, or we can somehow intelligently use the flexibility of DERs, existing ones and the new ones, in order to provide safe integration of DERs, but to increase cost and capacity as much as possible without investing huge amounts of money into strengthening and building new grid assets. Now, here is the graphical representation of some of these problems, just briefly. So backfeeding or reverse power flow in periods of light load and high penetration, high production of renewables. Then, do we need increased short circuit interrupting capability by the protected devices because of DERs? More importantly, do we need to adaptively change the setting and coordination of the protective equipment because of the changing conditions in the grid? Then also faults dropping out, inverters covering hidden load. So DSOs need to be aware of the hidden load at all times and able to manage it in an intelligent way. Then mobile storages in form of electrical vehicles, changing their locations in real time and causing load profiles to become highly dynamic, something that DNOs didn't need to worry about, traditional ones. Then utility distribution network planning for new investments or other ways to solve it, and voltage, power, harmonic, and other variations caused by intermittent sources of energy. So we can see completely new set of challenges faced by today's DSOs. We can conclude that that cannot be managed using paper-driven processes. So an intelligent and centralized management solution is must-have for emerging DSOs. Now look at this. Look at what the same governments that were incentivizing connection of as many DERs as possible are saying now. And please don't get me wrong, connection of DERs is great. We need to connect as much DERs, especially as renewables, as we can. But we need to do it in controlled and safe environment. So they're saying we will need a technological wonder to manage, operate, and control tomorrow's grids with so many DERs. Here is one passage from the report of one of the US governmental agencies for renewable energy. They're now saying, and this is from the last year, as DER penetration accelerates over the next decade, voltage control and grid stability will be the key challenges for distribution network operators globally. The answer, of course, does not lie in restricting further DER rollout, because DERs are great. However, the focus must be on a greater visibility and control of voltage at the point of load, and investment in technologies which both protect the consumer from the effect of high voltages and provide confidence to the consumer that her investment is wisely used. Thus, this will require implementing cost-effective smart technologies that dynamically manage DER while never compromising consumer safety. So this is this technological wonder they're talking about. And so we are coming to something called utility distributed energy resource management systems, or utility DERMS. Now with this slide, I would just like to briefly go through it and to avoid confusion, because in today term DERMS have become very attractive concept, very attractive term, and thus different vendors and even different stakeholders use DERMS for completely different software solutions aimed for different stakeholders and aimed for different goals. So we have DER management solutions aimed for transmission system operators with the main goal to enable balancing of supply and demand. Then we have DER management solution specifically aimed for distribution system operators to enable them to overcome the challenges caused by DERs and to enable them a swift transformation from inactive DNOs to highly involved DSOs. So to enable to relieve congestions and voltage violations, to defer or avoid capital investments, to enhance distribution grids hosting capacity by intelligently use the flexibility of DERs. Finally, to optimize the whole grid behavior with many DERs dispersed all over the grid, and to enable grid edge stability. Then we have DER management solutions aimed for market participants and prosumers with the main goal to economically optimize the production of various DERs. However, for the problem we are talking about today, for the management of distribution grids in an optimal way, for enabling smart grid transformation, this is what we need. And we call it utility DERMS. So utility DERMS is a centralized solution aimed to monitor, control, protect, and optimally coordinate the response of DERs on a global level, so on the whole distribution grid level, and be aware and able to solve all technical and other system-wide violations in real time. And here is the depiction of the EcoStruxure DERMS, utility DERMS solution developed in Schneider Electric. So you can see that it is a centralized solution, completely aware of the entire grid by having on its disposal sophisticated network model, aware of all the DERs in the grid from small scale ones connected on the residential units, such as rooftop solars, batteries in the houses, and so on, up to big DERs connected to the middle voltage level in the range of tens of megawatts. And more importantly, able to use the flexibility of all of these DERs in a coordinated fashion with the traditional resources, such as capacitors, load tap changers, voltage regulators, and so on, to optimally run the emerging distribution grids. So utility DERMS solutions should consist of several modules in order to enable a safe operation. First, DER monitoring and control. As we said, in order to enable this much needed awareness, DER monitoring is must have. Also, the ability for the DSOs to easily control the output of DERs in order to avoid congestions is a must have for DSOs. Then DERMS should consist of constraint management and grid optimization modules in order to enable operators to manage the constraints, to predict them and prevent them from happening, and also to use all the available resources in an optimal fashion. Then to utilize DER flexibility, aggregated flexibility of small scale resources and the flexibility of the large scale ones connected to the middle voltage. Finally, ability to defer or avoid capital investments into building new assets in order to host new DERs, but instead to use wisely the flexibility of the DERs in order to avoid constraints. So for a set of all these functionalities, a new term, active network management, or ANM, is coined. And fortunately, through utility DERM solutions, DSOs have a complete set of ANM capabilities at their disposal. Now let's see some of the examples of ANM through DERMS. First, DER awareness. So as we discussed, with so many DERs being integrated on a daily basis, DSOs do not have proper understanding of where are DERs, what is their current output, are the constraints violated because of DERs, then what are the forecasts, what is going to happen in near and midterm future periods. Fortunately, through DERM solutions, this much needed awareness is provided, which is consequently used for both real-time and look-ahead constraint management. Now here is the example from the EcoStruxure DERMS. First, here we can see a DER monitoring dashboard, and through these dashboards, a real-time and forecasted behavior of all the DERs in the grid is fully on the disposal of DSOs. So they're fully aware in real time what is going on with DERs in the grid. Most important key performance indices regarding DERs on the DSO's disposal. Then the critical points in the grid that can be caused by DERs forecasted behavior and ability for DSOs to react and prevent these critical conditions to happen. Then state of charge and capacity of batteries in real time, which is very important in today's conditions, because then DSOs can use this capacity of the batteries to provide the much needed flexibility for constraint management and grid optimization. Now, also very important, all types of DERs fully modeled in the network model. So besides having and knowing where are DERs and what types they are, measured and estimated real-time output of DERs on the DSO's disposal, refreshed in real time. As operated state of the grid, also refreshed in real time, so the operator is always aware of the conditions in the grid. Then, are there any violations caused by DERs with blinking of the elements, alarming, and other ways to let the DSO know so DSO can react? Finally, but very important, user-friendly ability for DSOs to connect or disconnect or manipulate with the output of DERs just by a click of the mouse. Then constraint management. As we already discussed, yesterday's challenges in distribution grids are nothing alike what we are facing today, and especially in the near future. Here, only the loading challenge is presented, so loading violations, but we have similar story with other violations such as voltages as well. So if you look at the first graph, we can see that in the passive distribution grids environment of yesterday, the only challenge regarding loading was peak loads in some highly predictable periods of a day that were very easy to be managed by yesterday DNOs by using traditional resources and traditional procedures. However, in today's highly dynamic conditions caused by DERs, besides having much higher peaks caused by electrical vehicles, especially superchargers, microgrids, and so on, we also have reverse peaks. As we discussed, in periods of light load and high production of renewables, we have reverse peaks. And even more importantly, these peaks are very hard to be predicted. It's not like in yesterday's conditions where we had almost no changes in load profiles and peak loads were very easy to be predicted. Now, This is very hard to be predicted. So DSOs need to be aware and able to react in real time. So by monitoring system conditions in real time and applying advanced DERMS real-time applications for constraint management and grid optimization, DSOs are able to use all available resources, including DERs, demand response programs, energy efficiency programs, and also traditional resources such as switches, capacitors, and so on, and to optimally mix all of these resources and their response to avoid congestions and other violations in the grid. Here is the example of the constraint management in EcoStruxure DERMS, a simple example where we can see two feeders here with some DERs connected to few of their buses. And here we can see that EcoStruxure DERMS is in real time updated with the measurements from SCADA and AMI from weather systems about weather data, and if exists from market platform about the schedules of the DERs. Now through power flow and state estimation applications, EcoStruxure DERMS calculates the state in the grid, and let's assume that at this moment it detects two violations. First, reverse power flow at the beginning of the feeder and over voltage at the point of connection of this big solar. So because at this moment loading is low and we have high production of this solar farm, we have these two challenges, and it is detected by the EcoStruxure DERMS. On these challenges, on these violations, automatic constraint management is triggered in the DERMS, which consequently calculates that there is enough flexibility in this energy storage here to actually consume and take the excess energy of the solar farm. And in that way, we have twofold benefits. First, we're going to solve the constraint violations. And second, also very important, we're not going to waste valuable energy produced by solar farm, but we will save it for our later use. So we're not going to curtail highly valuable solar. We calculated that we have in the energy storage enough capacity to take this excess energy in the critical period and save it for the later use. So now this new calculated schedule and set point for the energy storage is commanded directly to the energy storage, or if there is a market platform, to the market platform, and the violations are solved. Of course, it's also available proactively. So when the constraints are predicted to happen, for example, in 2 or 3 hours, the schedule of the energy storage is manipulated in order to proactively prevent constraint from happening. So now this is very simple example for the presentation uses. Of course, we have much more complex problems in today's distribution grids, but fortunately also successful ways to solve them through DERMS solutions. Finally, processing new DER connection requests and increasing the hosting capacity. So, as we said, distribution utilities, their planning departments are receiving huge amount of new DER connection requests on a daily basis, and it can be processed with traditional procedures. Then they need to see how to host these DERs without violating constraints and causing congestions. The traditional way would be that these requests would require huge capital investments into building new assets. Then, in order for these investments to be approved, it would need to go to the regulator. These processes, besides being extremely expensive, are also lengthy processes that can take up to 1 or 2 or even 3 years. And so in this traditional way, we are hugely deferring integration of DERs. So the question is how to host a maximal amount of new DERs but without waiting for lengthy approval processes? And the answer is use the flexibility of existing DERs and also offer flexible contracts to the new customers and use this flexibility to avoid congestions, instead strengthening the grid and waiting for their approvals. And through DERMS planning modules, we have on our disposal non-wire alternative ways to host new DERs. Now let's see the example. First, hosting capacity heat maps. These heat maps are basically coloring the geographic views of the grid per their ability to host new DERs. These heat maps are placed on a utilities web portal. Now, if I'm the customer and I want to connect, for example, let's assume 10 new PV farm of 10 megawatts at the specific location. Without this heat map, I would need to send the request to the utility. With having the heat map, I would log in to the utilities web portal. I would see, for example, that at this location, only 800 kilowatts is allowed to be connected. And of course, I'm not going to even send this request. It's fully unfeasible. I will think about changing the location and lowering my power and so on. But these heat maps placed on web portals significantly reduce amount of unfeasible requests and unburden planning departments. Now let's assume a different example. Let's assume that I'm a second customer and I want to connect 1 megawatt to this same location where 800 kilowatts is allowed. I inspect it on the web portal. I see that 800 kilowatts is allowed, and I conclude that it's almost feasible. I will send it to the utility and see what they are going to say. Now, as we said, traditional way for the utility would be to say, we need to strengthen the grid. We need to apply for the approval from the regulator. We need to wait for the regulator's response, which can take whatever time, and it can also be declined. However, with having DERMS and DERMS planning modules with so-called non-wire alternative applications, utilities can actually calculate in which specific periods these violations are going to happen because of this excess 200 kilowatts. And in most cases, this is just in a fraction of a day or even in a fraction of a month, the congestion is going to happen. With calculating this, utility can determine how to intelligently use the existing flexibility of the available DERs, and also to calculate what kind of flexible contract to offer to the new customer that will allow utility to manipulate with this excess 200 kilowatts in this fraction of a time, for example, 1 hour per month. And if the customer agrees and signs the flexible contract, the utility can approve the request. In that way, enhance hosting capacity because it allows additional DER to be connected. It also allows this DER to produce the maximal power in most periods, in 95% of the time. Just in this fraction of a day or a month or a year, when this excess power causes congestions, utility have the right, by signing the flexible contract with the customer, to manipulate with this excess power to avoid congestions. So utility DERMS solutions enable non-wire alternative ways to overcome violations. First, to sign flexible, to calculate what kind of flexible contract to sign, then to sign it with the customer, and then by having on its disposal real-time applications to exactly know at what periods utility needs to manipulate with this excess power. So in this way, first, huge amounts of money are saved because capital investments are avoided or deferred. And second, lengthy processes of approvals for new capital investments are avoided. So also twofold benefits. So now let's sum the main benefits of utility DERMS solutions. First, complete awareness of DERs. Complete awareness of what is happening in the grid in real time with high amount of DERs dispersed all over the grid that are changing their behavior in real time. Then managing all the constraints in real time in the automatic way. So predicting constraints, changing the schedules of the DERs, mixing this with manipulating with traditional resources such as capacitors, switches, low tap changers, and so on, and optimally running the grid and manage constraints. Then ability to be aware of the changing fault currents in the grid and ability to adaptively change relay protection settings and coordinations in real time based on the real-time conditions in the grid and calculated fault currents. Then to use flexible generation for system-wide balancing needs. In other words, to offer the aggregated flexibility of all the DERs to the transmission operators, and then transmission operators can use these flexible resources instead of turning on expensive, huge baseload power plants. Finally, to optimize existing equipment to limit, defer, or even avoid new, highly expensive capital investments by offering non-wire alternative functionalities and flexible contracts. Now, let's conclude what we talked about today. We know that today's power systems, and especially distribution grids, are going through tremendous changes, and it's obvious that emerging power systems will be nothing alike what we were accustomed to. Traditional distribution grids were passive networks without any complex and active elements, and were very easy to be managed without almost any interaction by DNOs. However, with the rapid integration of DERs in the last decade, this paradigm is shifting to a new world of complex distribution systems that could be efficiently managed only through highly involved and active participation of operators. So we need rapid change of the paradigm from DNO to DSOs. In this new world of high penetration of small active resources dispersed all over the grid, the reliability and efficiency can be maximized only if all these resources are well coordinated and optimally managed in a centralized fashion. Only if being aware of the whole system with all active resources and being able to react proactively or in real time on dynamic changes in the grid, system operators can enable safe and reliable operation of the grid. Fortunately, emerging DERMS software tools aim to offer all these capabilities and, in other words, enable much needed smart grid transformation or DNO to DSO transformation. Thank you very much for your attention. If there are any questions, I would be happy to try and answer.
Thank you, Dr. Rokas. I got few questions from audience. Okay, the first question, they asked you to comment on PV solar forecast accuracy and lead time.
Sorry, Dubček, can you please repeat the question?
Okay, they asked you to comment on PV solar forecast accuracy and lead time.
Regarding, okay. I understood PV forecast, but after that the connection broke, so I didn't hear it.
Yeah, the leading time.
Okay, so yeah, so nowadays DERMS solutions, I can talk about EcoStruxure DERMS because there is where I work in Schneider. So in today's forecasts that are part of DERMS solutions. All kinds of DERs, including PVs, are forecasted using artificial intelligence, using advanced algorithms such as similar day algorithms and so on, in order to predict soils as much as possible and to enable operators to be ready to react on the predicted conditions. But I would like to emphasize once again that besides having forecast through DERMS, DSOs are also aware of real-time conditions. So for example, if something unexpected happens that is not predicted, DSOs are again aware in real time and able to react. So first, the answer to the question: yes, DERMS solutions consist of intelligent and sophisticated forecast of all of the DERs, of course, in addition to the load forecast. So the state of the grid actually in the predicted time is calculated, not just forecast of the production, but forecast of the whole state and conditions in the grid for up to several days is calculated. By knowing that, distribution operators are also aware of the predicted constraint violations that are going to happen, and by having so-called look-ahead constraint management tools, they are able to change the specified schedules of the DERs in order to actually proactively solve the constraints. So based on the forecasted states, to change the schedules of the DERs and avoid constraints from even happening, which is very valuable because saves the assets of the distribution grids by not allowing constraints to even happen, and in that way prolongs the lifetime of the equipment.
Okay.
So I hope I answered, but if there is any more question regarding this, please.
So it looks like it emphasizes on the control actions or the corrective action when the contingency happens, right?
Not just when it happens. So I would not say that emphasis is on when the constraint violation happens. I would say that the emphasis is to prevent the constraint from even happening. But
Okay.
if something unpredictable happens, then also there are tools to solve it when it happens. So in my view, in more times, in 80% of cases, we will try to prevent constraints from even happening. But if something unpredictable happens, we are also fully able to solve it at the time of happening in real time.
Okay. And what are the algorithms or the process behind this software? For example, OPF or simplify OPF, or AI, or for the decision making, or the advanced optimization methods, or something else?
Advanced optimization algorithms aimed specifically for the structure of distribution grids, because as we know, the structure of distribution grids is completely different than transmission systems. So our algorithms are fully adapted to the specific structure and conditions in various distribution grids, such as one-phase elements, two-phase or mixed grids with both three-phase, two-phase, and one-phase elements, low amount of measurements, so much harder to perform state estimation than in transmission grids, and so on. So all of our algorithms are very sophisticated and based on distribution grid structure. I cannot talk about specifics of the algorithms, but what I can say is that they're highly sophisticated and aimed for specific structure of distribution grids and adaptable for different distribution grids. For example, in Asia, in Europe, in America, we have completely different structures of distribution grids, but our algorithms are fully proven at all of these places and able to calculate and optimize all of these grids.
So from what you say, it would require a huge computation power. So the computation time will be a problem for DERMS or not?
No, computation power is not such a problem. Of course, if we have huge distribution grids with hundreds of thousands of nodes, we would need stronger computation power, but it is not something that causes problems to the utilities. Utilities are aware that they need strong servers and strong computation power, but nothing special that they're not accustomed to. So I would not say that it's a problem, but yeah, distribution grids can be huge with huge amount of nodes. So sometimes the computation power can be, we would need a little bit more, but I would not say that it's a problem. We faced very, very big distribution grids in world, especially in Asia, with many, many nodes, and we are fully able to successfully run them and optimize through our solutions.
All right. One question from audience, is energy storage a must-have for constraint management?
I would not say that it's must-have, but it's very valuable asset. If we have it, it's very valuable. We can use it for many, many different cases for constraint management and grid optimization. We can optimize the grid and perform constraint management without it, with traditional resources and with using demand response, energy efficiency, and other programs, and also flexibility offered by third-party DR aggregators. But I would say that energy storages are very valuable asset, and my prediction is that the integration of energy storages is going to be a very big thing in near future. So I would say, yeah, it's very valuable asset, but it's not impossible to perform it without having it.
Yeah, and is this software? Can this software incorporate with the all controllable equipment in the system?
Yes.
For example,
Yes.
like voltage regulators or control capacitors, something like that?
Yes, the integrated part of our solution is also our SCADA. So we have our own Schneider's SCADA that is part of our DRUM solution that actually provides communication with all the resources in the grid. So through SCADA protocols and also through integration with third-party aggregators through internet protocols and so on, we provide full control and ability to dispatch all the resources.
All right. Another question: what are the key data required in order to conduct an accurate PV forecast?
The minimal kind of data is either weather forecast or some kind of history of the production of these solars. So either based on the weather, based on the history, based on the output curves, we can perform forecast. But of course, as many data we have, the more accurate the forecast will be. So I would say the minimal data would be either weather data or history of the production. But if we have both, and if we have other data as well, it would be much more sophisticated. When I say weather data, I mean irradiation, basically. Then if we have temperature, even better. If we have other data, even better. But irradiation is really important.
Do you have a typical figure for accuracy of the forecast so far?
Yes, we have data regarding accuracy. Unfortunately I can't talk about that, but I can say that the processes to get some kind of test data, we implemented in the algorithm, and then utilities, the test data is from history, and then they compare it with their accurate conditions in that period. And so far, our algorithms prove to be very accurate. I can't, because of the security and other rights, I can't talk about specifics, but yeah, we have data about that.
Okay. And could you explain more about the anticipated DER issues causing grid stability? And
Sorry, I didn't catch this question. Can you please repeat?
All right. Okay. Can you give me more details on the DER issues causing stability problems?
Yeah. So, but when we talk about the distribution grids, at least for today, we don't have the stability problems like in transmission grids that are going to cause collapse of the grid. What we call stability problems in today's distribution grids are actually voltage violations, increases, and over voltages and under voltages in the grid, and load problems. So those are basically the stability issues in distribution grids with this amount of DER power. So what can cause it? Intermittent sources can cause it. So they can cause overloads at their points of connection because they're hard to be predicted. So in periods of light load but high sun radiation, for example, they can cause overloads at their connection points and cause this kind of distribution grid edge stability.
And please clarify hidden load. What is the hidden load anyway?
Okay, yeah. So basically, hidden load is, or there are different terms for this phenomenon. So we have gross load and net load, or hidden load, however we want to call it. It is the production of renewables inside of the feeder. So we have measurement at the head of the feeder, at the feeder head, and with just this information, DSO would think that this is the load, the gross load in the grid. However, because we have renewables inside, for example, rooftop solars, they are producing one part of the load. So they're covering this load part from the DSO's awareness. This is what we call hidden load. Why hidden? Because if, for example, cloud comes and reduce or even completely reduces the amount of power produced by solars, then the load will suddenly highly increase. So the operator needs to know and needs to have this information about this so-called hidden load. So the load produced by DRs deep down in the grid, in order to be aware that it can be lost at any point because of cloud or because wind stops blowing, and be able to manage it in real time.
Okay. And another question, does this software come alone or come with the communication infrastructure or the SCADA infrastructure?
It basically, the whole package is with SCADA. However, we also can integrate with third-party SCADA. So third-party SCADA can, the data from the third-party SCADA can feed DERMS, and then we can communicate with the equipment through third-party SCADA. However, the preferred condition is if we deliver the whole package with our own SCADA.
Okay. Can you share the cost of the package, or
I
you have it now?
I can't because of many reasons, but one of the reasons is that I don't know because we have different packages for different utilities. It highly varies, but another reason is because my organization wouldn't allow it. So
all right, because that one's from the audience. All right. Okay, they will contact you later, or they will contact Schneider Electric later. Okay.
Yeah, and of course, if some of the audience have and remember some other questions, I'm always available. You can send me email and we can communicate through email or schedule meeting, whatever. I'm always available and happy to answer. So don't hesitate to contact me.
Okay. I didn't notice if you give your email address already.
Sorry, can you repeat, please?
So I'm not sure if you give us the email address.
Okay.
For,
Sorry.
for
Yeah.
audience?
Can I share it maybe on the chat, or can I
Can,
send you later and you can share it with audience if you are aware, or
yeah. Oh,
what
yeah.
is the best way?
You can also write down on your slide if you can.
Yeah, sure. That's the best way. Yeah, you're right.
Okay.
Here. Here is it.
Okay. Thank you.
You're welcome.
Okay. Because the many audience are so interested in your PowerPoint presentation. So do you have a version that you can share it publicly?
The presentation.
Yeah, the
Yeah,
version that
just
you can
please,
share.
can you give me a day or two just to check with my organization? Can we share all of the slides, or we need to remove some of them, and I will send it to your email. Is it okay?
All right.
Yeah.
Sure.
Great. Thanks.
So after I got the slide from the speaker, and then I will share to the people who want that by by emailing to me. Okay, you can email to me, and then I share you the slide.
No
Okay.
problem.
All right. So I think we out of questions, and this is a good session. Thank you very much. Thank you very much, Luca.
Thank you very much for hosting me, and thank you for everyone who joined. It was my pleasure to host this webinar. Thank you very much.
All right. So thank you all the audience. So you make this session successful. Okay. Until next
Thank
time.
you.
Have a nice day.
You too. Bye.
Bye.